Hello and welcome back to Reactor Heat Transfer. We're going to talk right now about tube bundles, flows across tube bundles. Now these are very important in engineering because they're used for heat exchangers, and these heat exchangers are for everything from power plants to electronics, but they all look the same on a given scale. So we see these in a wide range of gas heaters, boilers, things like that. The complication here is that the flow area changes as the flow moves across the tube bundle. You have larger flow area in between the tubes. So the gas velocity is going to change with some sort of periodic behavior. Now we quantify the geometry here with the tube diameter, which is the distance between the, across one single tube, as well as the tube pitch. Now, in aligned bundles like this one, where you have preferred flow lanes and so on, you have both a vertical pitch, which is the center to center distance, and you have a horizontal pitch or a longitudinal pitch, again, center to center distance. The issue with these is that the preferential flow path usually leads to degraded performance because the fluid doesn't mix very well. You also can use these staggered bundles, and here again you have the tube diameter, and then you have the horizontal or the vertical pitch, and you also can use either this diagonal pitch or a longitudinal pitch. So longitudinal, diagonal, and vertical. Now, for engineering applications, we're generally interested in the average heat transfer coefficient over the entire tube bundle, because the effect of the wake of the first tube bundle on following bundles means that heat transfer may be different in each row. But we can simplify the problem by just looking at the average over the entire system. So we have a familiar correlation, right, for the Nusselt number. We have to look very carefully, though, at the Reynolds number. The flow speed is based on what we call the minimum free flow area. So if we have an aligned arrangement, we define the maximum velocity based on the free stream velocity. The velocity here is our free stream velocity times some quantity that helps us characterize that change in flow area. And here you have the diagonal pitch, the diameter, the transverse pitch, and so on. So then we can go back to correlations. The Zakauskas correlation for tube bundles is a little bit different than the one for cylinders and so on. But it's valid for at least 10 rows of tubes. And we can use these empirical correlations for aligned and staggered tubes and so on and so forth. Now, in these kinds of systems, the fluid temperature can change from inlet to exit. We always want to evaluate the fluid properties at the average fluid temperature rather than the inlet temperature or the outlet temperature, to avoid any problems with using fluid properties that are not close to the average value. We can also look at the log mean temperature difference. As I said earlier, the fluid temperature can change as the flow moves through a tube bank because it's going to absorb energy. So using heat flux equals H delta T can actually overpredict the heat transfer if you use the initial temperature. The reason is because as the fluid moves along, the fluid temperature gets closer to the surface temperature, and the heat transfer is going to be degraded. So you could easily overpredict the total heat transfer. The way we avoid that is to use the log mean temperature difference. Now, the log mean temperature difference is defined as you see here on the slide, and basically what it allows us to do is write the equation a little bit differently. So we have the inlet temperature and the exit temperature here, and then we have this exponential function. So essentially what will happen is if this is the surface temperature of your tube bundle and this is your inlet temperature, you'll have this exponential function that eventually approaches the surface temperature if the thing is infinitely long. And so here we have the average heat transfer coefficient in the tube bundle, the number of tubes per row. Here's the number, or the number of tubes per row, the number of rows, the diameter, the pitch, the specific heat, and so on.